How do real electrical components differ from ideal Ohm's law? Imagine you're trying to follow a recipe perfectly, but the ingredients keep changing slightly each time. That's similar to how real electrical components behave compared to the simple rules of Ohm's law. Ohm's law states that the current flowing through a conductor between 2 points is directly proportional to the voltage across those points and inversely proportional to the resistance. It's written as V equals I times R. This law assumes that resistance stays the same no matter what voltage or current is applied, and that components behave predictably and linearly. But in real life, things are a little more complicated. First, resistors and conductors don't have perfectly constant resistance. Their resistance can change with temperature, frequency, or even the voltage itself. For example, when current flows through a resistor, it heats up. This heat can cause the resistance to go up or down depending on the material. Metals tend to have resistance that increases with temperature, while some materials like carbon can behave differently. So, resistance isn't always a fixed value as Ohm's law suggests. Next, real components like batteries and wires have internal resistances and other parasitic effects. A battery, for instance, has internal chemical resistance. This internal resistance causes some voltage to be lost inside the battery itself, so the voltage you measure outside is less than what the battery actually provides. Wires also have tiny amounts of resistance, which can add up in long circuits and cause voltage drops that don't match the ideal calculations. Some devices do not follow Ohm's law at all because they are nonlinear. Diodes and transistors are good examples. They only conduct current in one direction or change their resistance depending on the voltage applied. When you increase the voltage, their current might increase rapidly or suddenly, breaking the linear relationship that Ohm's law predicts. At higher frequencies, the simple resistance model isn't enough. Components like capacitors and inductors introduce reactance, which depends on the frequency of the signal. This reactance causes the current and voltage relationship to deviate from the straightforward V equals I times R formula. Instead, you need to consider how capacitance and inductance affect the circuit at different frequencies. Physical limitations also play a role. Small batteries or resistors have size and material constraints that limit how much current they can supply or handle. For example, a tiny battery might not deliver the current predicted by Ohm's law because of chemical and physical limits inside the cell. Environmental factors like humidity, contact resistance, and noise also influence real components. These factors can cause small fluctuations in measurements, making the actual behavior differ from the ideal model. In electrical engineering, Ohm's law is a fundamental tool for analyzing circuits, but engineers always remember that real components don't behave perfectly. They include additional factors like temperature coefficients, internal resistances, and frequency effects in their models. This helps ensure that circuits work reliably in real-world conditions, not just in theory. Knowing these differences is essential for designing, troubleshooting, and choosing the right components for any project.